Hello guys and welcome to another calculus video. This video is part 2 of the infinite summation guide, and in this video we're going to go over everything you need to know to evaluate this infinite summation of a rational function of n. So in this section of the video we're going to be talking about using partial fractions, evaluating telescoping series, using the zeta and eta functions as well as the digamma functions, and using the polygamma functions as well. I'm also going to have a few references to previous videos which go deeper into some of these topics and more methods that you can use to evaluate summations. And yeah, let's go ahead and jump right into the video. So using partial fractions. So if we have a rational summation, we're generally going to use partial fractions to break it down into smaller parts that we can then evaluate sort of one by one. The main difference between this and integration, as you can see here, is with integration, see, when we have 1 over x times x squared plus 1 dx, this will be decomposed into 1 over x plus negative x over x squared plus 1 dx. However, if we're doing a rational summation, it's actually going to be a little bit different because we're going to want to break it down all the way to its smallest parts. And what I mean by this is rather than stopping at negative n over n squared plus 1, we're also going to break that down into negative 1/2 over n plus I plus negative 1/2 over n minus I. And you'll see why we're going to do this in a little while. But essentially we're going to break it down to all of its linear factors and not leaving any quadratic factors in the bottom. So now let's go over some methods to evaluate the new decomposed series. So the main tool we're going to use here, well, not the main tool, but one of the main tools we're going to use here are telescoping series. So telescoping series are of the form the sum from n equals 0 to infinity of f of n plus k minus f of n, where k is just an integer. And these are super easy to evaluate. Basically, all you need to do is start writing out the first few terms until you see the terms start to cancel, which will sort of let you know about the pattern that the summation is going to follow. Then the sum is going to be equal to the leftover terms at the start plus the limit as n goes to infinity of the extra terms. So let's see what that's going to look like here. So in this situation, we have the sum from n equals 1 to infinity of 2 over n times n plus 2. So using partial fractions, this becomes the sum as from n equals 1 to infinity of 1 over n minus 1 over n plus 2. Now, when you go ahead and start writing out all the terms, we get 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6. So essentially what's going to happen here is after I've written out this many terms, we know that there's going to be more terms after that. But we're going to cancel everything that we see right here. Now something to note here is that this 1/5 and this 1/6, we haven't written out those terms yet. So if we were to continue to write that out, we would get plus 1/5 and plus 1/6, but we haven't gotten there yet. So these are canceling with something later on in the summation, while this 3 and 4 are canceling with what's already here. And notice that this 1 and 2, 1 and 1/2, are never going to cancel because there will never be another term with 1 or 1/2 in it later on in the series. So the overall series is just going to be 1 plus 1/2 since these won't cancel with anything. And then we have the limit as n goes to infinity of 1 over n plus 1 minus 1 over n plus 2. Actually, there should be a negative sign in front of this negative right here. And the reason for that is, remember I said that 1/5 and 1/6 didn't actually cancel with anything in our current series, and they cancel with something later on. Well, we have to keep into account these extra terms at the end that didn't cancel with anything. So in this case, we only summed everything up to n equals 4, right? This 1/4 means that we plugged in n equals 4. So our leftover terms when n was equal to 4 was negative 1 over n plus 1 and negative 1 over n plus 2, which is negative 1/5 and negative 1/6. And as we continue going on with the summation, we're always going to have those leftover two terms at the end, which is why it's important to have this limit as n goes to infinity right here. Now, in the case of 1 over n minus 1 over n plus 2, these two leftover terms are just going to go to 0 as we go to infinity, so they're not really that important. So overall, our summation is just evaluating 2/3. However, we do need to worry about those extra terms, and here's why. In this example, we have something very similar, except instead of 1 over n plus 2 and 1 over n, we have ln n plus 2 and ln n. And also, we're going to sum everything up to n equals 4. So we get ln3 minus ln1 plus ln4 minus ln2 plus ln5 minus ln3, so on and so forth. Now, these start to cancel right here. And then this ln5 and ln6 would cancel with something further up on the summation. However, we notice that these are sort of our leftover terms right here. So, if we take the limit as m goes to infinity of the partial sum from n equals 1 to m, which is the same as the summation right here, we're going to get, it's the same thing as the limit as m goes to infinity of these first terms, negative ln1 minus ln2, plus the leftover terms at the end, which notice that we had n equals 4 gave us ln5 and ln6, which means that overall, if we go up to an arbitrary integer m, it's just going to end up being ln m plus 1 and ln m plus 2, right? N equals 4, we have 5 and 6, so that's just 1 more and 2 more right here. And so notice when we add these two natural logarithms and take the limit as m goes to infinity, this limit right here actually goes to infinity because natural log of m plus 1 and m plus 2 both increase without bound. So that's why it's important to notice these extra terms at the end. Because even though, if we take the limit as n goes to infinity of ln n plus 2 minus ln n, we'd find that it would just be equal to 0. However, this summation here actually doesn't converge because of these extra leftover terms at the end. So if we don't take into account the extra terms at the quote-unquote end, we may get a false value for our series. So, for example, in this series, we might find that it was equal to negative ln2 when really it diverged. However, in general, as long as the series converges and limit as n goes to infinity of f of n exists, we can use telescoping series. And if the limit as n goes to infinity of f of n equals 0, we can ignore those extra terms. However, it's always good to just keep in mind that they're going to be there and do the limit anyway. Telescoping series are really good with rational functions. As you can see right here, I have two examples. In this situation, we had 1 over n plus 1 times n plus 2. And this is very similar to what we just did. So this telescoping series just ends up evaluating to 1. Because if you write out the terms, everything will cancel, and then the terms at the end go to 0. And all that really is going to impact us is that first term, which is 1 over 1 minus 1 over 2. So our overall answer is 1. And here, this is a little bit of a different story because we have 3 terms right here. But notice all we have to do is do partial fractions. We get 1/2 over n plus 1 minus 1 over n plus 2 plus 1/2 over n plus 3. And when we go ahead and we can actually split this into two different telescoping series. So 1/2 the sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus 2 minus 1/2 the sum from n equals 0 to infinity of 1 over n plus 2 minus 1 over n plus 3. And after evaluating both of these telescoping series, we get our answer to be 1/4. Now let's talk about the zeta function. So the zeta function is kind of an interesting function. We're not too concerned about the properties of the function. We're mostly just going to use it to represent values of our summations. So zeta of s equals the sum from n equals 1 to infinity of 1 over n to the s. And interesting values of the zeta function, clearly as s goes to 1, this is going to become the harmonic series, so zeta of s is just going to diverge at that point. However, zeta of 2 is known to be pi squared over 6, zeta of 4 is known to be pi to the 4th over 90, and zeta of 6 is known to be pi to the 6 over 945. Now, it's important to note that any value of zeta of 2n is known, and it's going to be some power of pi divided by some number. And any value of zeta of 2n plus 1, so any odd value of zeta is unknown, and so we just have to write zeta of 3 or zeta of 5 or whatever, because it's not going to have a known value. So the zeta function allows us to evaluate several useful infinite series, which are otherwise quite difficult. For values of s other than the ones shown, such as 3, we simply write zeta of 3, since there's no known closed form. So let's look at some examples right here. In this first example, we're evaluating the sum from n equals 1 to infinity of 1 over n plus 1 times n squared. This is the same after we do partial fractions as the sum from n equals 1 to infinity of 1 over n plus 1 minus 1 over n plus 1 over n squared. Now, this 1 over n plus 1 minus 1 over n is just a telescoping series similar to what we just did in previously. And this 1 over n squared, notice that this is the sum from n equals 1 to infinity of 1 over n squared, which is just zeta of 2, which is pi squared over 6. So that gives us our answer right here. Now a little bit of a more complicated example here is the sum from n equals 1 to infinity of 1 over n times n plus 1 cubed. And this is the same as the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Notice that this is again just the telescoping series, and we're also subtracting 1 over n plus 1 cubed and 1 over n plus 1 squared. So we evaluate the telescoping series to be 1, and both of these series here, they're missing the first term since they're shifted over by 1. So what I mean by this is zeta of s, as if we go back up, equals the sum from n equals 1 to infinity of 1 over n to the s. However, in this case, we have the sum from n equals 1 to infinity of 1 over n plus 1 cubed and 1 over n plus 1 squared, which means that we're never going to get that first term when n was equal to 1 of just 1 over 1 to the s. So both are missing the first term of 1. So what this means is that both of these series, for example, this first one is just going to be equal to zeta of 3 minus that first term, which was 1. So this series is equal to zeta of 3 minus 1, and this one is equal to zeta of 2 minus 1. If we go ahead and plug in the values here, we get that our overall answer is 3 minus zeta of 3 minus pi squared over 6. There are a few nice tricks that we can use with the zeta function to derive values of other infinite series. So, for example, if we take zeta of s equals n sum from n equals 1 to infinity of 1 over n to the s, and then we multiply by 2 to the negative s, notice that we now get 1 over 2n to the s. And 2n, the sum from n equals 1 to infinity of some function of 2n is just going to take the values of all the odd numbers, right? Or, all the even numbers. So, while zeta of s sums over all the odd numbers and the even numbers, this summation sums over only the even numbers. So if we subtract these summations, we actually get all the numbers minus the even numbers is just equal to the odd numbers, right? So that tells us that 1 minus 2 to the negative s times zeta of s equals the sum from n equals 1 to infinity of 1 over 2n minus 1 raised to the s power. Similarly, if we instead of multiplying by 2 to the negative s, we multiply by 2 to the 1 minus s, we get 2 times this original summation. So now we're taking the even numbers and the odd numbers, and we're subtracting the odd numbers twice. And what this leads us to getting is we get all the even numbers minus the odd numbers, which is actually just the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n to the s. We subtract the even numbers twice, so that means we get all the odd numbers minus all the even numbers. And this function is also called the Ada function. And you can just evaluate it with known values of the zeta function or just directly by plugging in. So these two generalized series can be very useful in evaluating rational summations, so let's look at some examples of how to use these. So here's an example with the Ada function. We have the sum from negative 1 to the n of over n squared times n plus 1. After performing partial fractions, we get these three summations. Now this first one, negative the sum from n equals 1 to infinity of negative 1 to the n over n. Now we're just going to use the sum of x to the n over n from n equals 1 to infinity equals negative natural log of 1 minus x. So we plug in that formula, and this just becomes ln2. For this summation right here, we actually have to shift it over by 1, because notice we're starting at n equals at n plus 1, not at n. So I'm going to shift the index starting at n equals 0 and then subtracting out that first term again, because the term when n equals 0 is just 1. Notice I also multiplied by negative 1, so I got negative 1 to the n plus 1. And notice that this series right here is the same as this series. They're just shifted over by 1, correct? So that means this is also just natural log of 2, as you can see right here, and we have to remember to subtract out that 1. And then this last series right here, negative 1 to the n over n squared, is the same as subtracting the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n squared, which is just eta of 2. So we plug in 1 minus 2 to the 1 minus 2, because s is 2 in this situation. And then zeta of 2 is just pi squared over 6, so we just go ahead and plug in that. And once we reorganize everything and solve, we get 2 times natural log of 2 minus 1 minus pi squared over 12. Here's another situation where we could use the other formula right here. If we have the sum from n equals 0 to infinity of 1 over n plus 1 half cubed, well, now we can't really use the zeta function because we're shifted over by 1/2. If we were shifted over by 1, for example, if this said n plus 1 or n plus 2, then we could just shift the index until we get something that looks like the zeta function. But in this case, we can't do that because we have 1/2, so we can't ever get that to look like an integer. However, what we can do is multiply by 8 on the top and bottom. And what this does is it gives us the sum from n equals 0 to infinity of 1 over 2n plus 1 cubed, which is the same as the sum from n equals 1 to infinity of 1 over 2n minus 1 cubed, which was just our expression that we derived earlier, which was related to the zeta function. So in this case, s equals 3, so we get 8 times 1 minus 2 to the negative 3, zeta of 3, which is just 7 times zeta of 3. Now comes by far our biggest tool when it comes to evaluating rational summations, the Digamma function. So the Digamma function is kind of interesting because it's not really related to summation, though as you can see here it's defined by summation. Its true definition is being the derivative of the natural log of the gamma function, which seems completely unrelated to summation, and in reality it kind of is. But because of this interesting definition here, we actually have a few ways to use this summation quite nicely. This gamma here is the Euler-Mascheroni constant, which is the same as the limit as n goes to infinity of h of n, or h sub n minus ln n. Now h sub n simply means the nth harmonic number, I believe. It's just the harmonic series. So the harmonic series is just the sum from k equals 1 to n of 1 over k. Now you know that obviously as n goes to infinity, this diverges, but so does ln n, and it turns out that these two numbers diverge sort of at the same rate, so that they have a finite difference as n goes to infinity, which is equal to gamma. It has a value of approximately 0.577. And so this is our digamma function. It has some useful identities here. For example, digamma of z plus 1 minus digamma of z equals 1 over z. And more interestingly, digamma of 1 minus z minus digamma of z equals pi cotangent of pi z. This one's also very, very useful. I'm not going to prove either of these identities. This one right here is super easy to prove just using this definition. This one right here is a little bit more involved, so I don't expect you guys to be able to prove it without knowing where it comes from. But for now, we're just going to go ahead and use the formula. So I've showed you this summation function right here, but how exactly are we going to use this function? I mean, it seems kind of random and not necessarily applicable to rational functions. Well, let's see how we're going to use it. So if we have this summation from n equals 0 to infinity of 1 over n plus a minus 1 over n plus b, what we're going to do is we're going to add and subtract gamma in the front. Now technically we don't really need to do this because we could just use an alternate definition of the digamma function without using gamma, but I find it easier to just use the digamma function directly since it's such a nice and useful function. Next, what we're going to do is on the inside here, we're going to add and subtract 1 over n plus 1 right here. Notice that I highlighted all these blue ones and all these red ones right here. So we're going to separate all the blue terms and the red terms. Now note that we can separate these summations right here because each of the summations are going to be convergent after we do the separation, so that is justified. So we get negative gamma plus the sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus b, and then plus gamma minus the summation from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus a, which is just digamma of b minus digamma of a. So if we're able to figure out or calculate the value of digamma of b and digamma of a, we can evaluate this infinite series quite easily, even if a and b are not very nice numbers. This can be extended to a general case using the same reasoning. So we have a sum from n equals 0 to infinity of a1 over n plus b1 plus a2 over n plus b2 plus a3 over n plus b3 all the way up to some number k. This is going to be the same as negative a1 times digamma of b1 minus a2 times digamma of b2 minus ak times digamma of bk. As long as a1 plus a2 plus a3 all the way up to ak overall equals 0. Which actually has to be true if this summation is going to be convergent, which is not too hard to show if you guys want to go ahead and do that. So that means that we can represent pretty much any rational summation, actually, no, not pretty much, almost any rational summation as a sum of digamma functions. The only time we're not going to be able to do that is if we have some squared term, like for example n plus b3 were squared. That cannot be represented in terms of the digamma function. You can use identities or tables of values for the digamma function in order to find its values, or you can use the same strategy, this should say u, Doesn't matter. You can use the same strategy featured in one of my previous videos to calculate summations. I'll link it as a card in the corner right here. That video is very, very interesting, and we will go over the methods used in that video in the next video in this series, but I definitely suggest you go ahead and check it out if you want to go ahead and evaluate these summations without directly using the Digamma function. In the other case, if you don't want to find these identities or tables of values, you can choose to leave your answer in this form right here with just a sum of different values of the Digamma function, and that's totally okay because in many cases you may not be able to actually find the true values of the summation. But in general, I prefer to try and evaluate those values of the Digamma function in order to have a more satisfying answer for my summation. So here's an example right here. The sum from n equals 0 to infinity of 1 over 4n plus 1 times 4n plus 3. Now, what I'm going to go ahead and do is, first of all, I divided by 16 so that this was n plus 1/4 and n plus 3/4. Then, after doing partial fractions, I got 1/8 times the sum from n equals 0 to infinity of 1 over n plus 1/4 minus 1 over n plus 3/4. And this is just the same as digamma of 3/4 minus digamma 1/4 all over 8. Rewriting this, we get 1 over 8 times digamma of 1 minus 1/4 minus digamma of 1/4. And then we can use our identity from before for digamma of 1 minus z minus digamma of z. So we're just going to get pi over 8 cotangent pi over 4, which is just the same as pi over 8, and that's the answer to this very, very nice summation. Here's another cool example that shows us how the digamma function can help us deal with complex numbers. We have the sum from n equals 0 to infinity of 1 over n squared plus 1, which is the same as the 1 over 2i times the sum from n equals 0 to infinity of 1 over n minus I minus 1 over n plus I. Then we take 1 over 2i times digamma of I minus digamma of negative I. We're going to replace digamma of I with digamma of 1 plus I minus 1 over I. And the reason we're allowed to do this is using that recurrence relation for the digamma function. Now, the reason we did this is because now, notice we have this digamma of negative I over here, and we have digamma of 1 plus I over here. Which means that if we set z equal to negative I, then we now have digamma of 1 minus z minus digamma of z, which means we can go ahead and plug in that formula for digamma of 1 minus z minus digamma of z. So we get 1/2 plus 1 over 2i times pi cotangent of pi times negative I. And once we go ahead and use our trig to hyperbolic identities, we get that this summation is overall equal to 1/2 plus 1/2 pi hyperbolic cotangent of pi. Notice that this was literally just 2 lines for evaluating a very gnarly summation with complex numbers, and that's just the power of these identities for the digamma function. Now let's talk about the polygamma functions. So the polygamma functions are very closely related to the digamma function. When we differentiate the digamma function, notice that the digamma function can also be written with this little 0 right here. And the reason for this is when we differentiate it, we just put a 1 right there, indicating that it's been differentiated one time. So if this is the digamma function, this is the second polygamma function right here, also sometimes called the trigamma function. It's not used nearly as often as the digamma function, but if you go ahead and differentiate, you get this nice formula right here. Sum from n equals 0 to infinity of 1 over n plus x squared. Notice we can keep differentiating, and we could get digamma with a little 2 up here, and that's equal to this, and you can keep going, and you'll get generalized formulas for sort of zeta functions, but shifted over for any integer value of s. They're not quite as useful as the digamma function, but they can be nice for representing the value of the summation as a value of these functions. Also, you can differentiate the identities of the digamma function to find identities for these functions. For example, if we take this identity right here, we differentiate, we find that trigamma of x plus trigamma 1 minus x is pi squared times cosecant squared of pi x. Typically, we're going to use these functions to represent the answer to a summation where no other closed form exists. For example, the sum from n equals 0 to infinity of 1 over n plus 1/3 all squared is just equal to trigamma of 1/3, and there's no other way to evaluate trigamma of 1/3, simply because with most of these functions, they don't have very many values that are known. So for example, trigamma of 1/3, it's just trigamma of 1/3. There's no representation in terms of other constants. you could also look right here. This summation 2 over n plus 1/4 cubed is just negative, I guess this would be tetragamma, but we'll just call it the second digamma function, second polygamma function right here of 1/4. And again, there's no real way to evaluate the second polygamma function of 1/4. So we just write our answer like this, and that's the whole answer because there's no other way to write it. However, occasionally there will be some way to express our answers in terms of other known constants. So for example, the sum from n equals 0 to infinity of 1 over n plus 1/4 squared is a trigamma of 1/4, which, using the identities for the trigamma function and also some other tricks, you can find is equal to 8g plus pi squared. Note that g here is Catalan's constant, the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 squared. This is super important to remember. It's pretty straightforward to use, since just whenever you see this summation, you're going to think, okay, it's Catalan's constant. And the reason it's a named constant is because this series shows up everywhere, and there's no way to express it in terms of other constants. So something else that you may want to see, some other videos that have very, very, very useful information on methods for evaluating rational infinite series. I have a video on calculating values of the digamma function, and you can use the same strategies in this video to directly evaluate certain rational summations without having to use the digamma function as an intermediary. And also, messing around with this interesting function is another video that I have that discusses another function that's very useful for evaluating alternate series. I'll go ahead and put a card in the corner for both these videos. Both of them discuss important supplemental methods for evaluating infinite series if you want to learn more. And without any further ado, let's get on to the practice problems. So here are the first 9 right here. Go ahead and give them a shot. And I'll use this as a moment to go ahead and ask you guys, if you wish, you can go ahead and join the Discord server. And if you have any trouble with these practice problems and you can't figure them out, I encourage you to go ahead and join the Discord server, and I can try and help you to evaluate these problems so that you can learn more. Yeah. So hopefully you were able to figure out all of these problems. Please note that if they don't seem to have any way further to go, some of them may have an answer that's just in terms of the polygamma functions, which is perfectly okay if you can't evaluate it from there. And here's our last few practice problems right here. Go ahead and try these. Just a reminder that this right here is just the identity for g. And the sinc function right here, sinc of x is just sine of x over x. Alright, well, I hope you guys were able to evaluate all of these summations with number 13. Hopefully you just left it in terms of the digamma function. So I hope you guys enjoyed the video. This was a lot of fun. Oh, I'll go ahead and discuss what we're going to talk about in the next video. So in the next video, we're going to talk about infinite products and using them to evaluate infinite series. We're going to talk about polylogarithms, using integrals to evaluate infinite sums. We're going to talk about using the beta function, the partial sum trick, exchanging the order of summation, and other special functions such as the Lurch transcendent and hypergeometric functions. So I hope you guys enjoyed the video. I hope you learned a lot. Again, if you need any extra help, go ahead and join the Discord server and I can see what I can do. So I hope to see you in the next video, and hopefully you learned a lot in this video as well. So thank you so much for watching. See you in the next video, and bye.